Okay, this is going to be our sixth and final video in our work and energy series here. So it's going to be a very short video, at least as far as new content goes. I only have one last little topic for this video, and that's going to be power. We'll talk about that in a sec. After I'm done with talking about power and doing a quick example with it, I'm going to quickly go over a bunch of the topics that we covered in this module. We've covered a lot of ground in these six videos here, and I just want to make sure that we all can sort of absorb it in one quick review here. So I'll do a little review going over some of the equations that we looked at, and then we'll move on from there. Okay. So on to our last topic of work and energy here, and that is going to be power. So power is pretty simple. Power is just defined as the rate at which work is done. So in other words, power is just this equation that we see here. Power is just work over time. The SI units for power are watts, and 1 watt is 1 joule per second. Okay. And so the easiest way maybe to take a look at this will just be to do an example. So let's do an example here. Or in this example, we want to well, we're going to be taking a look at this system here. So what is the power output for a 60 kilogram woman who runs up a 3-meter high flight of stairs in 3.5 seconds, starting from rest, but ending with a speed of 2 meters per second? Okay, and so let's start off by just remembering that we want to find the power, which is just work over time. And how are we going to find the work done by this woman? Well, let's write down the equation, this conservation of mechanical energy equation, where we are considering the work done by a non-conservative force. So let's write that down here. We have, from our last video, we're going to have the kinetic energy initial plus the potential energy initial plus the non-conservative work done has to be equal to the kinetic energy final plus the potential energy final, right? And so here, what do we have going on? Well, initially we have no kinetic energy, right? The woman starts from rest. She's also starting at ground level, so she has no potential energy, gravitational or otherwise. This non-conservative work, I'm going to call this W. This is the work that's being provided by the woman's body, right? Her legs are pushing, she's running up these stairs. So this is the non-conservative work done by an external force here, by her working on the system of her moving up these stairs, right? So this is going to be the work that we're looking for. What's our final kinetic energy? Well, we know what our final kinetic energy, we're told that we're going to have some velocity at the top of the stairs, and it'll be equal to that. And the only potential energy that we're going to have at the top of the stairs is potential gravitational energy, and so we're going to have an mgh here. Okay. And so quickly, just simplifying this, we end up with W, our work done by the woman, is equal to 1/2 mvf squared plus mgh. Okay. And then really it's just a matter of substituting this into our power equation, and so we end up with the power output that this woman achieves is 1/2 mvf squared plus mgh all over t. And then we just need to substitute in numbers. So maybe I'll just quickly write it out. We end up with 1/2, her mass is 60 kilograms. The final velocity is 2 meters per second, but that's squared, so 2 squared plus mg h is 3 meters. And over the time that she did this, which was, let me clean that up a little bit, which was 3.5 seconds. Okay, and if we plug that into our calculators, we're going to find that her power output was 538 watts. Okay, so that's how we would use this power equation, and that's sort of our power example. Okay, so as I mentioned, I'm also going to do just a quick little handwritten review of some of the equations that we looked at in this module. This is sort of just meant to really jog everybody's memory and put it all in one place, so we can sort of think about it in one sort of train of thought here. So we started off the chapter talking about work. We defined work in this way, where the work done by this force F is equal to the magnitude of the force times the displacement experienced by whatever is having the force done to it times the cosine of the angle between them, right? And this was just a definition. We then mentioned that, well, we can think about a single force and the work done by that single force, but we can also add up all those forces to get an expression that looks like this, right? So we can add up all the forces and then we find the net work done on this thing. We then went on and defined the work energy theorem, right? So the net work done was equal to 1/2 mv squared minus 1/2 mv initial squared. And we saw that we named each of these terms. We called this the kinetic energy final, and this was the initial kinetic energy, right? And so this was the change in kinetic energy. Okay, and so from that same discussion, we wrote down this general expression for kinetic energy. We also defined two types of potential energy. Let me just mute my mic here for 1 sec. Right, so we also defined two types of potential energy. We defined potential gravitational energy in this way, where h was the height off the ground, right, wherever we're setting our 0 point to. We defined spring potential energy from Hooke's law, written like that. So these are both potential energy, and this is kinetic energy. We then saw that through conservation of mechanical energy, I'll abbreviate it like that, conservation of mechanical energy, we saw that we can write kinetic energy initial plus the potential energy initial has to be equal to the kinetic energy final plus the potential energy final. And this is true if no non-conservative work is being done on the system. But then this brought in the whole discussion of conservative versus non-conservative forces, right? So conservative forces can have potential energies associated with them, right? And we did this for the gravitational force. We did this for our spring. We also talked about non-conservative forces. And these ones cannot have potential energies associated with them, right? But then through talking about non-conservative forces, we talked about non-conservative work being done, and this led us to our sort of final form of our equation, our conservation of mechanical energy, but now considering non-conservative work being done on the system, and we ended up with the equation that we've been using a fair bit here toward the end of this module, which I'll write down right here. That's supposed to be a P. Okay, that's kind of terrible, but in any case, so we ended up with this equation, and what is this equation telling us? Well, this equation is telling us that whatever our initial kinetic energy is, and whatever our initial potential energy is, in whatever form that initial potential energy may be, spring energy, whatever, gravitational, doesn't really matter, whatever our initial kinetic and potential energy summed up, plus the non-conservative work done on the system, has to give us our final kinetic energy plus whatever our final potential energies are, okay? And we're going to find that that is a very useful equation to solve a number of problems, okay? And so that's basically it for this module. I just wanted to sum everything up here, and that'll do it for work and energy. We'll move on to something new in the next video.